Hi guys, so I, Baharun, will be guiding you through the first section of Unit 1, which is power function. What is a polynomial expression? A polynomial expression is an expression in the form of ax power n plus ax power n minus 1 and so on until a0, which is a constant. However, this expression has certain properties like n, which is the power of the variable x, has to be a whole number. And a0, a1, a2 are all real numbers too. And the leading coefficient is determined by the variable with the highest power. So here's an example of a polynomial expression. X power 4 plus 3x squared minus 2. So what is a polynomial function? A polynomial function is very similar to a polynomial expression. Only difference is that the function you are able to include the dependent variable, which is fx. But however, it shares the same properties like a polynomial expression. And what is a power function? A power function is the simplest form of a polynomial function, which is fx is equal to ax power n. And such examples can be 4x power 3, x squared, and hx is equal to 1. However, hx is equal to 1 is a power function, even though a lot of people get confused by it because it has a variable whose power is 0, and anything power 0 is equal to 1.
Well, let's look at the different types of power functions, and let's carefully look at their graph features. On the left side, we have a constant function of y is equal to 2. Its graph features are domain, x contains all real numbers, range, y is equal to 2. As x approaches infinity, y stays at 2, and as x approaches negative infinity, y still stays at 2. It moves from coordinate 2 to 1 and has a line symmetry at y-axis. While on the right side, we have a linear function of y is equal to x, and its graph features are domain, x contains all real numbers, range, y contains all real numbers. As x approaches positive infinity, y also approaches positive infinity. As x approaches negative infinity, y also approaches negative infinity. And the graph extends from quadrant 3 to quadrant 1 and has point symmetry at the origin.
Well now, if you look at the quadratic graph, you'll notice it shares similar features of the constant graph. That's because they're both even degree power functions with a positive leading coefficient. And if you look at the cubic graph, you'll notice it shares similar features of the linear graph. That's because they're both odd degree power functions with positive leading coefficients. And the same applies for the quartic and quintic graph. If the quartic has a positive leading coefficient, it will share the same features as the quadratic graph, previous one. And if the quintic has a positive leading coefficient, it will share the same features as the cubic graph in the previous slide.
Now let's look at the power functions with negative leading coefficient. If you look at the right side, the quadratic function, you'll notice that the domain x contains all real numbers and the range y is less than or equal to 0. And as x approaches positive infinity, y approaches negative infinity, and as x approaches negative infinity, y approaches negative infinity. It extends from quadrant 3 to quadrant 4 and has line symmetry at y-axis. On the left side, if you look at the cubic graph, you'll notice that its domain x contains all real numbers, its range y contains all real numbers. As x approaches positive infinity, y approaches negative infinity, and as x approaches negative infinity, y approaches positive infinity. It also extends from quadrant 2 to quadrant 4.
See, that wasn't so bad, and you're almost about to finish 1.1. Just keep in mind that the features you saw in the even degree power functions with negative leading coefficient applies to all even degree power functions with negative leading coefficients, and the features you saw for the odd degree power functions with negative leading coefficients applies to all odd degree power functions with negative leading coefficients.
So here's the basic summary for finding the key features of power functions that have an even degree and an odd degree. So here's an example for finding the key features of the graphs of power functions. For the function y is equal to x squared, its domain is x contains all real numbers, range is y contains all real numbers but it's greater than or equal to 0. Symmetry, it's line symmetry at y-axis. And behavior, as x approaches positive infinity, y approaches positive infinity. As x approaches negative infinity, y approaches positive infinity, and this thus extends from quadrant 2 to quadrant 1. Question time. You have 45 seconds to solve, starting now.
Hi everyone, I'm Jayu and today we will be learning about the characteristics of polynomials. First, we will learn how to find finite differences. There are two methods for this. The first method is by constructing a table and using a graphic calculator. The second method is by using the degree and the sign of the leading coefficient. The equation that we will use for today will be y equals negative 2x to the power of 4. Okay, so by using the first method, we start off by creating a table whereby the x values are already listed. We then find the y values by subbing x into the previous equation. From there, we take the first value and subtract the second value to get our difference. Continue to do so until we can get a constant value for all our finite differences. From here, we can see that it is our fourth finite difference with a constant value of negative 48. Now we shall see how to create a scatter plot. By using your graphic calculator, key in your x values into L1 and your y values into L2. After finding our finite difference, we must remember that the numbers above do not correspond with the finite difference number. Now, let's create our scatter plot. We go to Stat Plot and select the first one. Then we choose On and Scatter Plot Type and enter. Click on Graph and tada, you will have your scatter plot. For a polynomial function of degree n, where n is a positive integer, the nth differences are equal, have the same sign as the leading coefficient, and is equal to a times the degree polynomial of the permutation, whereby a is the leading coefficient. Now let's try out method 2. By using the same equation, we know our degree is 4 and our leading coefficient is negative 2. As said before, the degree and the finite difference is the same. Therefore, it is the fourth value. And by using permutation, we can find out the finite difference. Therefore, it is negative 48. By using either methods, you can get the same answer. When we are asked to state the characteristics of a polynomial function, we must state the n behavior, number of minimum points and number of maximum points for either local and global, and also the number of x-intercepts. Now let's compare the characteristics of odd polynomials. We can see that both graphs have the same n behavior, which ends in both opposite directions. However, for the first one, it extends from quadrant 3 to quadrant 1, and it has no local and global points. However, it does have 3 x-intercepts. Now for the second graph, it extends from quadrant 2 to quadrant 4. It has 1 local max and 1 local min, but it has no global maximum or minimum points. And it has 1, 2, 3, 4, 5 x-intercepts. Let's compare the characteristics of even polynomials. We can see that both ends in the same direction. However, for the first one, it extends from quadrant 2 to quadrant 1, and it has 1 local max, but it does not have a global maximum point. However, it has 2 global and it has 2 local minimum points. It is also the two x-intercept points. Next, we can see that the second graph extends from quadrant 3 to quadrant 4, and it both has one local and global maximum point. It is also the x-intercept. Question time. Here's the solution.
Hi everyone, I, Jianmeng, will be guiding you to chapter 1.3, Equations and Graph of Polynomial Function. So, the first definition is an order. An order is a polynomial function that has a factor of x minus a that is repeated n times, which means that if the degree is n, x equals to a is a zero of order n. The next is the odd function. All odd functions have rotational symmetry that satisfy the equation f minus x equals to fx, means that when the graph rotated 180 degrees, the graph should be the same. Third is the even function, and all even functions have line symmetry that satisfy the same equation as the odd function, that is f minus x equals to fx. So, if let's say the graph at the left side reflects to the right side, that should be the same. So, what can we get from the graph? Usually, there is 4 things we can get from the graph. The first is the degree of the polynomial function. Second, the sign of the leading coefficient. Third, the end behavior. And last is the x and y intercept. For example, in this graph, you can know that this is an even function. And even degree polynomials are either facing up or down. Here is another example. As we can see that the graph which both the ends is at the opposite side. This is called an odd degree polynomial function. As you know, there is rotational symmetry on. For the sign of leading coefficient, we can see that there is 4 different kinds of graph. The left side of the graph is the even function, but there are 2 different graphs. The graph is on the x-intercept is the positive even function. The graph that is below the x-intercept is the negative even function. For the right side is the odd function graph. The graph that starts from negative y-intercept to positive is the positive odd function, and the graph that starts from positive y-intercept to negative is the negative odd function. For the end behavior, we can determine through the graph whether it's positive or negative by which is extended from which quadrant to which quadrant. For example, positive even function extends from quadrant 2 to quadrant 1. For negative even function, it extends from quadrant 3 to quadrant 4. For the odd function, a positive odd function that extends from quadrant 3 to quadrant 1. But negative odd function, it extends from quadrant 2 to quadrant 4. Finally is the x and y intercept. Again, a polynomial function has a factor of x minus a that is repeated n times, then x equals to a is a zero of order n. Here is another example. The equation is square of x plus 5. So, minus 5 has a zero of order 2 and x equals to 2. Here is a fun example for everyone. There are 5 questions on it, and try to solve it in 1 minute.
Hello everyone, I'm Vivian and I'll be guiding you through the subtopic transformation. After this study, students are able to state the transformations by looking at the new equation, transform graphs from the new equation given, and able to state the transform points through mapping notation. This is the general equation that you will find in the transform equation. These are the examples of the transform graphs. The red one are the new transform graphs and the black one are the original graphs. Example 1. This is an original graph of y equals to x squared. A. When a is negative, it experiences reflection in x-axis. When a is more than 1, it will experience vertical stretch with factor of a. And when a is in the middle of 0 and 1, it will experience vertical compression with factor of a. These are the examples of the transform graphs when a is equals to 2 and when a is equals to 1 over 2. K. When k is negative, it experiences reflection in y-axis. When k is more than 1, it experiences horizontal compression of factor 1 over k. and when k is in the middle of 0 and 1, it experiences horizontal stretch with factor 1 over k. This is a transform graph of k equals to 2 and k equals to 1 over 2, where the first graph is k equals to 2 and the second graph is k equals to 1 over 2. B. When b is positive, it experiences horizontal shift to the left by b units, and when b is negative, it experiences horizontal shift to the right by b units. This is the example of b equals to 2 and b equals to negative 2. You can clearly see that the x-axis, the x-intercept is negative 2 and 2. C. When c is positive, it experiences vertical shift upwards by c units, and when c is negative, it experiences vertical shift downwards by c units. This is the graph when c equals to 1 and c equals to negative 1. The y-intercept at the first graph is at 1, and the second graph is at negative 1. For reflections, when a equals to negative, it reflexes at the x-axis, and when k is negative, it reflexes at the y-axis. Note, the other word for shift is also translation, so do not be panicked if you see the word translation instead of shift. Notice that everything in the bracket is transformed horizontally and everything outside of the bracket is transformed vertically. New points can also be found through the new transform equation based on all points through mapping notation. This is the example of new transform equation through mapping notation. Finding new x is divided by k because any transformations with k, either stretch or compress, it is always 1 over, and when x multiplies in, x will take over the place of 1. It's negative b because whenever b is positive, it is shifted to the left, and when b is negative, it is shifted to the right, which is of opposite direction. Finding new y is multiplied by a because any transformations with a, either stretch or compress, is always multiplied with a. It's positive c because when c is positive, it is shifted upwards, and when c is negative, it is shifted downwards, which is of the same direction. A, k, b, and c are called parameters. The parameters that changes the shape and position of the graph is a and k. The parameters that do not change the shape but only changes the position of the graph is b and c, where b controls the left and right, and c controls the upwards and downwards. Reflections can only occur in parameters a and k, where negative a is reflection in x-axis and when negative k is reflection in y-axis. The width of new graph depends solely on value a and value k, where both the restrictions are of the same. If the graph is wider, a will be from negative 1 to 1, and k will also be from negative 1 to 1. If the graph is narrower, a will be from negative infinity to negative 1 and from 1 to infinity. And k will also be the same, which is from negative infinity to negative 1 and from 1 to infinity. Order of transformation is usually read from left to right, but most importantly, reflection, stretch, and compression have to be done first before any shifts. Real-life application. This is an example of real-life application. The area of a cuboid is represented by the equation Vx equals to x plus 3 squared. The graph of the equation is shown below. Question. The dimensions of the cuboid is multiplied by 2 and added by 3. Find 1. The new transform equation. 2. New point if previous point was 0, 9. 3. New transform graphs. These are the solutions for the question.
Now, let's learn about the average rate of change. After this study, students are able to determine the dependent variable and independent variable. They will also be able to find the slope of the secant line of 2 points with the correct formula. Students are able to interpret the slope in correct units. A secant line is a line that connects 2 points on the graph. In other words, it is a line that cuts the graph on 2 points. It is not to be mistaken with a tangent line, which only cuts through 1 point. Finding the average rate of change is equal to the change in y over the change in x. If the answer found is positive, then the rate of change is increasing. If the answer found is negative, then the rate of change is decreasing. If the rate of change of any 2 points on the graph is the same, it means it has a constant rate of change. In other words, it is directly proportional. If the rate of change of every 2 points on the graph is different, means it has an inconstant rate of change, either increasing or decreasing with x value. The average rate of change between 2 points is equal to the slope of the secant line between 2 points. The unit will always be y unit over x unit. It is usually interpreted in a way whereby average rate of change of y with respect to x when x is given two x values is the answer. Or y is increasing or decreasing depend on whether it is positive or negative in the average rate of answer from given two x values. For example, if you are given a graph whereby you have x and y, you should determine the independent variable and dependent variable. They will also ask you to find a change or the average change for intervals. We should also know that the x value will always be your independent variable and your y will be your dependent. So now let's solve this together. We know that the independent variable is x and the dependent variable is y. Therefore, your independent variable would be time, whereas distance would be your dependent. To find your change in radius over change in time, we should look at intervals 0 and 5. Let's locate them. 0 and 5. We take y2 minus y1 over x2 minus x1, and therefore we get the answer of 5 meters per second.
Tangent is a straight line that touches one point of a curve on a graph. An instantaneous rate of change, also known as IROC, correlates with the slope of a tangent to a point on a curve.
So, there's three ways of determining an approximate value for an instantaneous rate of change at a point. The first one is a graph, second, table of values, and last is the equation.
So for the graph, you need to draw a tangent line on the curve and find its slope to find the instantaneous rate of change at a specific time.
So for the table of value, you need to pick the closest point that relates to the question. So the question is, the table above shows the distance of a jogger recorded at 1 second intervals. Estimate the jogger's velocity at 3 seconds. So to solve it, we must use the point close to 3 seconds to estimate the jogger's velocity. So the velocity is 7 minus 5.5 divided 4 minus 3. That it will equals to 1.5 per 1 meters per second.
By using an equation, you have to use the specified independent variable by the question and pick the closest independent variable and use them as an interval for average rate of change to determine the instantaneous rate of change. Looking at the above calculations, as the time intervals decreases, the average rate of change becomes closer to 36. Thus, the velocity of the jogger after 6 seconds is approximately 36 meters per second. Here's a question. Use the function 4t power 3 to determine a speedboat's velocity after 40 seconds. And here is how you solve it.